What I would like to talk today is about shock algorithms, but I will be talking about the kind of problems where shock wave generates and could lead to severe deformation, and in cases there will be damages in the materials. So I'm going to introduce a mesh-free method to solve these problems. It's a reproducing kernel particle method. This work is sponsored by the US Army Engineering Research and Development Center, Sandia National Laboratories, and a Japanese company, Asahi Kasei. So as a motivation, let me show you a few examples here. The one in the middle is the most obvious, that when the explosion happens, and if you watch it very carefully at the very beginning, you will see a shock wave propagating in the air, and very quickly they're gone. So they propagate in extremely fast speed. And what happens when shock wave hits the structure, that's what you see on the right-hand side. And here, it's a different testing facility. This is not the field testing, but it's something called a blast simulator, which is a facility at the center that I'm working affiliated with. So as you can see, this is a so-called actuator. It's an array of actuators, and each I think there are 4 to 16 array of actuators that you can arrange in a different configuration, and each actuator can be activated and produce up to 12,000 psi in a few milliseconds. All right, and you can adjust the motion of different the front of the actuator to generate different shock profiles. Right. So for example, if you want to simulate the shock that is very far away, then the shock front is like a planar wave. Right. Then this will be like the motion will be like planar. But if the explosive is very close to the building, in this case, this is a column. Then there's a curved shock front. And one can actually use computation to give a prediction of the shock front and then use that as a control of this facility, right? So this is much better than doing it in the field, because something like this, you see the beginning and you see the end and nothing in between. You only see the fireball. But here you can see all the details of how the structures failed, how the cracks are initiated, and then propagate and leads to a structural failure. But what I would like to talk about today is more on this type of a problem. This is called explosive welding. I'll get into some more details about the physics of the problem at a later time. But what it does is it uses small explosives to generate very high impact velocity between two pieces of metals. And this is the only welding process that has been classified by NASA JPL as the kind of welding process that has very good bio-barrier protection, and also the strength of the material. In fact, you will see that it's actually the welded material could have a strength higher than the parent material, because this is so-called a single-phase welding. And so it's a very unique welding process that has been used by NASA for example, collecting samples from space, from other planets. Right? And this is the only one that will make sure that the material in the containers will not leak out and will not contaminate. But the key phenomenon in all these problems are shocks. And shocks really leads to very high strain rates, gradients, large deformation, fracture, damage of material, as a consequence of a very strong hydrodynamic effects. And shock wave propagates with discontinuities in density, in pressure, material velocity, internal energy. Right? So these discontinuities are propagating in space, similar to fracture problem, but they propagate in a really fast speed. And the shock front, the shock speed is very important, a very important quantity that when we do computation, it has to be very accurate. Otherwise, you miss a lot of important physics in the problem. And the key mechanics in these problems are Hankin-Hugoniot jump conditions, the second law of thermodynamics, and Hugoniot response. Okay, so now in order to model these problems I mentioned earlier, the shock wave could initially be in the air or could be in the solid and propagate to the solids. And the solids could deform in various different ways. So when one tries to model this kind of a problem, in terms of discretization, there are different ways of doing it, and we'll see in the end can we unify them. But the first one is the most common one in solid mechanics. So here I use the open circles to denote the mathematical points. And I use the solid circle to denote the material point, right? So in the Lagrangian description, that's a standard way of doing large deformation problem where you have the mathematical points that moves together with the material point. And you can imagine that, so here I have a circle demonstrating the support of a kernel function, which I will introduce in a minute. A kernel function determines the locality of the approximation and also defines the neighbor of a given, for example, point I in space. And you can imagine that once the approximation functions are constructed within this support, a compact support, then they deform with the material. They move and they deform with the materials. So basically what you do is you construct a set of approximations for all the nodes, and then all you do at the later time is just do a mapping through deformation gradient, right? So this is pretty obvious, and all you have to do is to construct a set of approximation at the beginning. And one can formulate the conservation laws, the Galerkin equations by either total Lagrangian formulation where everything maps back to the undeformed configuration, or updated Lagrangian, and they are equivalent anyway mathematically. But the whole point is just by mapping of the approximations, right? So as you can imagine, this approach will break down when the inverse of deformation gradient does not exist, and that happens when you have fracture, damage, fragmentation type of problems. Okay, then so we term this semi-Lagrangian and still carries the term Lagrangian. And so the sense of Lagrangian where at point I, the mathematical point at point I is still moved with the material point I, okay? But the shift function supports do not attach to the material. So you could have different neighbors at different state of deformation. So this gives you the flexibility of redefining the neighbors depending on the mechanics of what's going on in the physics of the problem, right? So for example, when crack happens, you can redefine the neighbors depending on the crack orientation and so on and so forth. But still, the mathematical points are still attached to the material point. You just you define the supports at the current configuration. And the last one is a typical one for fluid problem. It's an Eulerian kernel where the mathematical points are fixed in space and material points can flow in and out. And again, you define the kernel at the current configuration and once for all. And if you look at the difference between these three discretizations, really the difference between them is really the distance measure between a point of evaluation x and the material point xi. Here I'm using capital X as the standard notation to denote the material coordinate, meaning the material position at the undeformed configuration. I'm using a small x to denote the current position of a given material point. And so in Lagrangian kernel, really the distance measure will be measured at the undeformed configuration. And Eulerian one will be at the current configuration, the last one. The semi-Lagrangian is a little bit, so this is where the distance measure is defined at the current configuration, but it's still following material point I, right? So that's why this is moving with it, but the distance measure is defined at the current configuration. And that's really the main difference between semi-Lagrangian and Lagrangian. Okay, so now with this, as you will see, that in the pure Lagrangian or pure Eulerian approach, once you construct the kernel once, in this case at the undeformed configuration, in this case at the fixed point in space, then you are done for all. you just have to make sure that you have sufficient neighbors, and I will show you that having a sufficient neighbors it's necessary to construct the approximation. Whereas in the semi-Lagrangian kernel, because the neighbors could change, so you either redefine the support at every time step, which can be expensive, or you do something else. And so that's what I'm going to first address this, and then I'll get into the shock physics of the problem. Okay, so in terms of the discretization, so this is how you discretize the domain by a set of points, and approximation functions are expressed in terms of the multiplication of the kernel function, the red one in red, and the basis functions, and this is the sort of a standard construction under the framework of reproducing kernel. And the coefficients B's are a function of position, right? So this is not a standard least squares, and you obtain the coefficients B by enforcing this approximation will exactly reproduce the basis, right? So if you have monomials as the basis, you enforce this be able to exactly reproduce the basis. So the number of bases here will be the number of equations I have here in order to obtain B. And this is where you could get into trouble, because this means that this set of equations will have to be linearly independent. And you could have in the situation where, let's say, for example, if I take a case where I introduce linear basis, right? So in three-dimensional, I have a constant term and linear in x, y, z. So I have 4 terms here, 4 basis functions here. So here you have 4 equations. And that means at any evaluation points in space, it has to be at least be covered by 4 kernel functions like this. And these kernel functions determine the locality, that's the support, and also smoothness of the approximation. And depending on different kinds of spline functions here I introduced, that you get that the same order of continuity. So continuity comes really easy, in fact comes free, and the locality is controlled by the support size, but this could have a problem where you may not have enough coverage of the neighbors when you have higher order bases. And suppose if I'm using linear basis in 3-dimension, that means any position in space has to be covered by at least 4 kernel functions for the 4 equations to be linearly independent. And that means that when I solve this system of equations, that will involve a moment matrix that will look like this. It's a gram matrix of this set of bases and with respect to this kernel function. So that's the standard gram matrix. You have to make sure that the support coverage is enough so that this moment matrix is non-singular. And so that could be a problem for semi-Lagrangian approach. And so to resolve this issue, so here we introduce moving these squares as a regularization of reproducing kernel. Try to address the issue when there's not enough coverage of the neighbors, which could happen in a very large deformation of the materials. Okay, so in this case, I have these squares terms, 2 least squares terms. The first one is a standard moving least squares construction, right? So you take the nodal value and approximation of U, you take the square difference between them and weight it by the kernel function. And then here we add the second term in blue, which I'm going to show in a few minutes that I will be using also with this kind of construction. All the evaluation, all the integration points will be at the nodal points. So all the nodal points will carry state and field variables. Okay, so they all be computed at the nodal points. And in order for this construction to be unconditionally non-singular, all you have to do is in this approach, we add a few evaluation points close to the nodal point, and then take the difference between these functions, square that, and with the positive constants in front of it, right? So now you minimize this. So you minimize this residual, and again, just like moving these squares, you set x bar and move in space, and now finally you get this approximation function. And so in the end, you get an approximation function that looks just like a standard reproducing kernel, except that the moment matrix now has been regularized, and has been regularized with this additional term, m star, and you can show that, you can actually prove that as long as these few extra evaluation points near the nodal point forms a non-zero volume, meaning that they are not on the same plane, then you can prove that this is unconditionally non-singular. And notice that you might feel, well, I have some extra calculation, but this is really just to formulate, to construct the shift function. These few evaluation points are used in the construction of the shift function. All the state and field variables are still stored at the nodal points. Okay, so to see how this works here, I take, again, another pretty standard benchmark problem, the Taylor bar impact problem. And let me get back a little bit here. So when in the original approach, when there's no m star here, when m becomes singular, one simple approach to address that is to reduce the order of bases, right? And you can imagine if I had just constant bases, that means I have only one equation. I don't have to worry about solving a system of equations. And since my evaluation point is at the nodal point, there'll always be one coverage of one node, regardless. So having a constant basis, there's no issue. But once you go to the higher order, that's where the issue is. So one can consider, well, whenever there's no enough basis, simply use constant basis, right? So here I have three cases here. The first one is to simply use constant basis throughout the whole domain. And this way, then, the moment matrix is always non-singular. But unfortunately, with this, you see the numerical fracture here. Now, the second approach is to start with linear basis throughout the whole domain, and with the support size defined that you have sufficient number. But when the material hits the boundary and when deformation becomes too big, that the fixed support size will not have sufficient coverage for at least 4 neighborhood points, then you switch those points, the basis in those points, to constant basis. Okay, so that will also guarantee the moment matrix being non-singular, but again, when you do that, you introduce discontinuities in a domain where you have linear basis and another subdomain where you have constant basis. And that discontinuity actually generates another wave propagate, so you have actually artificial wave propagation induced from the interface. And that also doesn't give good results. And the last one is to stick with the linear basis and introduce the regularization that I just mentioned, quasi-linear basis, and no need to readjust the support and run nicely and compare very nicely with experimental data. Okay, so now coming to shaft physics. Okay, so here I'm taking a simple scalar problem as a starting point. So this is one on the left-hand side is a first-order conservation equation. F is a flux, and in general, F could be a function of U. So a standard or a typical shock wave problem with a scalar variable is the Burger's equation, right? So the Burger's equation, for Burger's equation, F will be 1/2 of U squared. Right, so when you have f being 1/2 of u squared, you take a derivative of x, it will give you u times u comma x. So if this term is u times u comma x, it's a first order wave equation, but with the wave speed being not a constant, but the wave speed being u, right? So wave speed is function of the solution. So you can already imagine when that is a situation, then it depending on the initial condition. If your initial condition in the space organization is such a way that the value of u of a given point on the trailing side is higher than the u on the leading side, then the wave on the trailing side could catch up the wave on the leading side and then forms a shock front. So that's a sort of an easy way to understand why shock forms. And then there are a few other important things. The shock speed is really the ratio of jumps between the flux and U itself. So the jump of flux, it really is the driving force. The jump of flux is the driving force of the wave of a shock wave. And then there's an entropy condition that you have to make sure that the shock speed is always in between the characteristics. F prime will give you the characteristic on its left-hand side, on its right-hand side, and that's the entropy condition. Entropy condition also determines whether there will be a shock forming or whether there will be a rarefaction. And for that, so if you don't have the right entropy condition, you could lead to a non-physical rarefaction like this and doesn't capture the shock. It misses the shock completely, right? So here, again, I'm taking that simple scalar first order conservation equation, but dimension-wise, and now I put it in multi-dimension. So now this becomes a divergence of the flux. And so in here, and this is what I was talking about. Okay, so now I'm going to say look at in one direction. That so this is a given point. Okay, and then you have a shock speed that is driven by the jump of the flux, and then you have a characteristic on the left-hand side. 1 over lambda will be the wave speed. And so if you look at the one in this case, the characteristic on the left and the characteristic on the right, if the slope on the left is higher than the slope on the right, or the characteristics, then they will converge and forms a shock. Whereas if the characteristic lambda on the left, the slope of that is less than the characteristic on the right, then they never emerge, and that's the rare fashion. Okay, so this determines whether the shock will form or the shock will not form. And this needs to be properly captured, and otherwise you miss the shock dynamics completely. Right, so start with the conservation equation and then the Eulerian equation. And here, as I mentioned, because of the type of problem that I need to solve, I would like to stick with nodal integration. Okay, so simply integrate these at nodal points. Right, so this is just a nodal point evaluation of all these state, the trial function, test function, and also the divergence of the flux. And this is the one that now we do something about it. So the flux is going to contain a solution of U, and that's where all the shock information is going to be in this term. Right? So really, this is the most important term. So instead of taking a direct evaluation of the divergence of the flux, here we take the smooth one, and this one is defined for a given point I. Is defined by the boundary integral, of this given point I. Okay, and so this comes back to the earlier work, the stabilized conforming nodal integration. We use this approach for two reasons. One is that this gives you, if these boundary integration cells are conforming, then you can show that this approach with nodal integration and then with the divergence computed this way will give you the first order variational consistency. So here the variational consistency refers to the consistency between the order of completeness in the approximation and the order of exactness of the Eulerian solution. Okay, so that means that if I have linear basis, if I say use linear basis, such as linear finite elements, I have first order completeness. I want to make sure that the Eulerian solution is exact up to the first order, meaning, and that's our standard patch test, right? So standard patch test is to say linear patch test. If I have linear finite elements, regardless of the element shape, I would like to get an exact solution for a PDE where the solution is first order. And that's where you can define all those patch test problems. And so this will give you that, so we call that the first order variational consistency. And if you do a nodal quadrature, okay, it doesn't have to do Gauss integration. In fact, Gauss integration may not satisfy this. With this kind of support that I have in the reproducing kernel shift function, they overlap each other. So Gauss quadrature would not give first order variational consistency with linear basis, but this will. As long as all these boundary integration cells are conforming, okay? And so we like this property. The second thing is that I can now then introduce the shock physics at the cell boundary, because as I mentioned, shock physics comes from the flux. The jump of flux is the driving force of shocks. And so I don't want to take another derivative of flux, because then again you got to do differentiation, and that depending on your discretization, right? So we want to have the shock to be calculated directly from some techniques which are introduced a few minutes. So this also avoids you to take another derivative of f. And so okay, so here also if these boundary integration cells are conforming, then the flux is conserved. Very easy to see that. And so then on the cell boundary, as you can see, as I said, so now on every point on cell boundary, you have a cell on the left, you have another conforming cell on the right. And then, so I'm going to pick up all the information from xi and the one to the right. There, I have to look at the characteristics. And then, depending on the characteristics, as I mentioned earlier, and also the jump of the flux, it will determine whether there will be a shock forming or rarefaction, right? So that's for this simple scalar problem, you can easily determine it this way, depending on shock speed and depending on the characteristics on the left and the right. And so that's where you can easily get your, this is called a Riemann solution of solving the Riemann problem. So this becomes the initial condition for you to solve the Riemann problem. And with the Riemann problem obtained, then I'll plug in the Riemann solution of the flux into this boundary integral. No derivative is taken, and that's how I then obtain the divergence of the flux. And the divergence of the flux, as I mentioned, is critical to shock propagation. Okay, so here's an example. I'm taking the Burger's equation, right? So in Burger's equation here, this flux is 1/2 of the u squared. Right? So initial condition is this smooth function. And again, as you can see, for example, on the right-hand side of the profile, right, u is larger on the left-hand side than u is on the right-hand side of any given point. So the right-hand side of this profile will generate a shock, whereas the left-hand side of the profile is opposite, and it will form a rarefaction, right? So you can see, you see the right-hand side start to form a shock, and this is the standard RKPM. You will see a severe oscillations. That's another thing which I'm going to touch upon in a few minutes. That's the discontinuity. So as you know, if you have a smooth approximation, that's the invitation of Gibbs phenomenon, right? So smooth function of smooth polynomials and try to capture something that is discontinuous. That's the source of oscillation. That's the Gibbs that we also need to resolve. But I will show you by standard SCNI, it in fact resolve also this the Gibbs phenomenon, and I'll explain in the next slide why that's the case. But anyway, here I also have a comparison with some Godunov's solution and Lex-Franchik's solution with much higher mesh density and okay, as a reference solution. Okay, so what I just did. Is remember I do nodal integration. So in a sense, what I'm doing here is whenever I'm looking at the shock conditions, and I look at the one on the left, the cell on the right, and I'm really taking the nodal value from the nodal points on the left and the right. So in a sense, what I'm doing here, I'm taking a cell average of U on each of the cell. And this is, in fact, consistent with the Godunov's theory. It says that to avoid Gibbs at the discontinuity front, the easiest way to do that is to use as low as the order of approximation as low as possible. So when I do nodal integration, what I'm doing here is I'm introducing a piecewise constant approximation to evaluate U on the left and on the right of this, on the cell boundary, right? And then from there, then I use the cell boundary information and I obtain the Riemann solution, and then from there I compute the divergence of the flux, and that's the driving force of shocks. But again, still doing it this way, as you can imagine, I have only first order accuracy. So one way to improve this is to consider, well, a piecewise linear approximation. And but then right away, you use first order, then you know, and you can test very easily. This actually violates the Godunov's order barrier theorem. The proof tells you that there will be an oscillation, there will be a Gibbs. And so that's, if you simply do a first order expansion as I have here, this is going to have an oscillation. So what we have done to improve the situation is I now modify this first order expansion by two things. First, I replace this gradient by a smooth gradient. Okay, so if there's an overshoot and undershoot situation, you can imagine if I take the boundary contour integral on that, it reduces that overshoot and undershoot situation. And then we introduce a flux limiter, right? So this is from the idea of a Van Leer. And so the idea is I skip all the details. This is between 0 and 1. The main idea is that you don't want a variation of the neighborhood points. You look at the neighbors, And you don't want the variation of U between the neighborhood points and the point itself to be more than the extrapolation of U from the nodal point. And so this is also consistent with the DVT concept in finite difference that people do, right? The vanishing total variation. There is a similar control of that. And so that's what we did. And so here I show you a 2D Burger's equation. How much time I have? Just want to make sure.
About 10 minutes.
10. Okay. Okay, so, right, so here, because of initial condition, this will form shocks on this interface, this here, and here, and here. Okay, so I need to go faster. So here I compare Riemann-SCNI with piecewise constant, Riemann-SCNI with piecewise linear, and as you can see, you clearly capture the shocks much sharper than the one that is more smeared in the piecewise constant approximation. Now, if you change the boundary condition to this, then in this case, in these two boundaries, there will be a rarefaction, and the shock will only form in this boundary. And now you can see that I'm having, again, with piecewise linear, Riemann-SCNI captures the shock front much better. Now it comes to nonlinear solids. Okay, so again, shocks come from the pressure term, which is the volumetric part of stress. So we separate the stress into the deviatoric and volumetric. And this is the weak equation. So we'll do another integration by parts for the volumetric part to get the gradient of pressure. And the gradient of pressure is, again, according to what we have just discussed, that's where we'll introduce the Riemann solution. And the Riemann solution will be on the cell boundary. And this is now done by, again, the boundary, the contour integral of pressure over the cell boundary. And that will give you the gradient of the volumetric part of stress. And this is how the jump conditions are introduced, right? So again, I have a boundary point here. I have a cell on the left and the right. And now, as I mentioned, now for the nonlinear solids, I need to meet this Hinkin-Hugoniot jump equation. And so you can construct a jump condition on the cell boundary point with the cell on the left and this on the right, right? So two jump conditions will allow you to solve for two solutions, P and U, pressure and velocity on the cell boundary. And that's the one with the star. Right, so two jump conditions give you that. So this will satisfy the jump condition. And then with this, you then plug this into the entropy condition, and there will be, if it's nonlinear solids, there's some nonlinear iterations that you need to do. And there are many really good Riemann solvers available that you can just use them. So you can then just combine this with Riemann solver. You get the Riemann solution on the boundary, and again, a contour integral of the Riemann solution of pressure on the boundary will give you the divergence of pressure. Right now, so far I have been using these cells as the sort of a mechanism for me to do all this, the jumps and all that. But this could be a problem with the applications that we have in mind, because constructing all these conforming cells, such as Voronoi cells, in this kind of a process will be just way too expensive. So what we have done here is we relax this contour integral on this conforming cell by the contour integral on the non-conforming cell. And obviously, this is going to violate that the variational consistency, as I mentioned earlier. But fortunately, we had a later paper that we showed that you can actually make a correction. You start with this, and there's a way to correct the gradient, the divergence of the flux at the nodal point, and still recover this variational consistency. So I'll just skip that for the interest of time. And with this, I can just solve this as a standard weak form instead of additional integration by parts when I'm working on this. So this is a standard weak form. Okay, and again, the volumetric part is the one that generates shocks. So you can now discretize this and get the internal force associated with this. And if you go through the algebra, so this is a pressure, you go through the algebra if you introduce partition of unity of the approximation function. So if you have constant basis, you at least have partition of unity property. You should also have the partition of nullity of the approximation function, meaning the sum of the shift function derivative should be exactly 0. You bring in these two properties, you can cast this term into a pairwise operation and sum up on this. And so it'll be pressure between point I and point J, and then this geometric parameter beta ij, and through this consideration, beta ij will be just it looks like just like this, and the gradient of the shift function again is computed by this contour integral, right? So, and the Riemann condition is now imposed in the middle. Okay, so with this we have a few test problems. I'm going to go really quickly through this just to show that okay, these have been validated, and now Eulerian. So standard Eulerian conservation law. So everything is the same as before, except now you have this advection term here. You still have the pressure term on the flux, and the advection term is right here. And now this is for the air, and here you can use ideal gas or JWL for the explosives. Okay, everything is the same on the pressure term, but here we have an additional advection term. And the additional advection term is computed also by boundary integral over the Voronoi cell. And since this is Eulerian, right, so everything is fixed in space, so I can still use this conforming cell. And because of the advection term, we introduce upwinding, and with this additional wave speed correction to minimize the smearing effect in this standard upwinding technique. Okay, so here's the shock tube problem. And here we have a comparison with this Riemann-SCNI piecewise constant. And the one that I just mentioned is called a monotonic upwind scheme for conservation law, or I have an extra E here. Anyway, that's the piecewise linear. We also compare to Weino scheme, again, this is additional E. The Weino scheme, this is one of the most accurate solution for solving shock problem. And as you can see, this muscle SCNI compares very well with Weino scheme 5. This is with DVT and also the third order Ranch-Kuda, right? So this is really good, but this one is very expensive. This is much faster to compare, although we can actually get very similar solution as Weino 5. I also look at the convergence rate. And so again, with piecewise constant and piecewise linear, so everything agrees with the theory on convergence. Right? So here we tested some problems where there's a shock generating in air, and so there's some vortex form, and shock refraction and diffraction are all nicely captured compared to some experimental data. This is double explosions. Here I have double explosions, and they generate the shock front, and they interact. Again, these are the experimentation and computation. So the last thing is that, well, if I now wanted to unify this with the shock propagation in the air and in the solid, well, can I unify them by just everything with Eulerian? Okay, and if everything with the Eulerian description, even for the solid, then with the Eulerian shock formulation that I just mentioned, it will just work. Just directly plug into this approach, right? So I have a solid here, and then I have an Eulerian grid. And the solid will, of course, going to be also discretized by some points. And so here, what we do is we will then use the solid points as the integration points, and then use the Eulerian grid to construct the reproducing kernel shift functions for U. So U is constructed by the background Eulerian reproducing kernel shift function constructed on the fixed points. The solid point here serve as integration points. And since I'm using this nodal integration, so the nice properties of nodal integration allows us to compute this and with solid points as integration points, and they are moving over through the Eulerian grid. I'll show you the performance of that. And so these Lagrangian integration points they are used to now carry all the state and field variables. And so I will have a pressure computed at the solid point, and they are moving, and they will be first projected onto the Eulerian grid by many different approaches. But here you can simply take the least squares minimization. And once I have here, they projected onto the Eulerian grid, and Eulerian grid now are approximated by the reproducing kernel shift functions. Then you can use the standard one that I just mentioned. Again, convert the flux on the boundary integral, and everything else carry through. Right, so here, let's first test some static problem here. So this looks like NPM, but NPM will use the background grid. First of all, NPM is with the finite element discretization and approximation on the background grid. They also use the background grid integration points, such as Gauss points, to do the quadrature. But here, the quadratures are by nodal integration with the solid points. Okay, so here I test the problem here, if I use FEM for the background, just like a standard NPM, and use the solid points, which is not at the integration the quadrature point, you actually get something similar to cross-cell instability. This is RKPM on the background, and with direct nodal integration or RKPM with SCNI, you get much better solution. This is the convergence by using more and more RKPM background. And you get the right convergence with this approach, with RKPM, with SCNI. And we can create a situation where the solid points are not matched with the grid points, with the background, right? So this obviously, and these red points are the integration points for the background grid. And in this case, actually, there's no solution. The solution diverges in FEM. And this, you still get really good results. All right, so here we test the problem where I have a Eulerian one, and which is background, which is FEM, and then RKPM on the background and also on the foreground. And you see, they get the right response, and then impact problem. Let me just quickly move to explosion. Is 5 minutes okay? Okay, so explosion problem, explosive welding, right? So generate the flux, generate the explosives. With the explosive that generate very high impact velocity, and with the control of the right angle, you will generate a jet. And this is necessary to peel off a layer of material to remove any contamination on the materials. It also, if the impact velocity is high enough, and since this is not by heat, right? This is, of course, plasticity, plastic deformation also generates heat. But it's not high enough to melt the material. So this is so-called a solid phase approach where it has a very small heat effective zone. So the welded material can be actually at least the strength same as the parent one or even stronger, because if the impact velocity is high enough and if the angle between the two plates are properly adjusted, which in our case we use numerical simulation to adjust that, then you can actually get the material in the interface that's stronger than the parent material, because the impact velocity with the jetting, it peel off the impurity of the surface. And with a very high impact velocity, you can have the two materials get closer with a distance smaller than the atomic spacing. So in the end, you could have the bond strength, which is higher than the original material. And so the key features to capture here are the jetting, because it's important to remove the impurity, and also this waviness pattern, because that create more contact surface, also provide a better interlock of the two pieces of materials. So we want to capture that. So the first example is following an experiment that is done not by explosives, but by magnetic field, right? So a high magnetic field, but this can only be done with the very small samples, because the magnetic force cannot be as high as the explosive. But anyway, this gives you a very clean setting for experimentation. And so we model, so this will impact with the one at the top, and we model the jetting here, and it also forms the vortex, right? So here we have a three level of mesh refinement just to check the convergence, and this is how this vortex are formed. If we have a comparison with experiment, right? So this is the tail, because that also provides an additional, lock-in between the two pieces of materials and the wavelength of the material. And this is the explosive welding, right? So this time the explosives are put here. This is PETN-based explosive, and they ignite it, and then they generate shock, and the shock will then propagate to this plate. It will then hit the bottom plate, and generate the jets. Okay, all right. So that's the simulation. Again, it forms the jet, and then you have all this wave generated on the interface. Right, so this is the leading point, and these different wavy pattern at different locations. And again, we have a comparison with experimentation, and they seem to agree reasonably. So in the end, that's my conclusion. I have introduced different RK discretization for Lagrangian and Eulerian, and finally find a way to try to connect them, and the approach taken hopefully will introduce a good numerical approach for various type of extreme events modeling. Okay, with that I conclude my talk. Thank you very much.